Throughout the technological age of modern medical sciences, innovation in the diagnosis of disease has been more prominent than ever. In this, various technologies have been developed under the field of imaging. Whilst many forms of imaging have been implemented throughout history, none have been as efficient as magnetic resonance imaging, or MRI in abbreviation. MRI technology is a medical device widely used in the identification of various illnesses, usually related to organic tissues. These can include cancers, tumors, strokes, or torn ligaments, to name a few. MRI is a form of radiology that uses magnetic technologies to view the human body. However, whilst there are many positive applications of this technology, there is an undisputable array of limitations which have obstructed its further uses both domestically and commercially. MRI technology was invented in 1977 by American physician and medical practitioner Raymond Damadian. The original machine understandably differs significantly in contrast to the modern MRI machine. However, the founding concepts remain the same. Magnetic resonance imaging is achieved due to the properties of protons, which are abundant within organic material. Protons exhibit a small magnetic field induced by their spin, in which can be manipulated by strong external magnetic forces. In the case of an MRI machine, a strong magnetic field is introduced. This introduced magnetic field changes the proton orientation in the direction the external magnetic field is traveling. A radio frequency pulse is then introduced, disrupting the proton, which then forces its orientation, usually in reverse to the external static magnetic field. As this radio frequency forces the proton against its nature, the proton will store energy to then be released as electromagnetic radiation once returning to its original orientation. This is achieved by turning off the radio frequency being emitted. This discharged electromagnetic radiation, whilst being non-invasive in living organisms, can be detected in an MRI imaging system. Computing technologies are then able to differentiate various tissues based on the rate at which this electromagnetic energy is released. As already observed, many forms of waves are used in the processes of magnetic resonance imaging, exemplifying their importance beyond a theoretical abstract. To satisfy a strong enough magnetic field, MRI machines use a unique form of magnet known as a superconducting magnet. These superconducting magnets consist of many coiled wires in which electrical current passes through, generating this strong magnetic field. To sustain a strong magnetic field within an MRI machine, usually being 2 Tesla in magnetic strength, means high energy levels are required. This is achieved with the aid of superior conductive technologies known as superconductors, in which reduces the resistance to almost zero. Liquid helium is used to induce an absence of resistance and is usually less than -270 degrees Celsius. This is then insulated by a vacuum to prevent temperature disruption due to conduction or convection from the external environment. The strong magnetic field delivered by these superconductive magnets enables highly accurate and effective imaging capabilities. However, a limitation to this is the expensive componentry, not only in the manufacture of the magnet, but the liquid helium fuel required for its operation. One of the main advantages of magnetic resonance imaging is its safe operating mechanisms, but more importantly, its invasive spectrum-free scanning system. This ensures that radiation-vulnerable patients, such as pregnant women and infants, can be safely analyzed without compromise of accuracy and efficiency. In relation to accuracy, magnetic resonance imaging is a highly effective method in identifying body structures such as soft tissues like ligaments and cartilage, and organs such as the brain, heart, and eyes. MRI technology also allows the ability to accurately study blood movement in the circulatory system, identifying potential coagulations which could lead to stroke or heart attack. Whilst MRI technology outmatches most forms of modern imaging mechanisms, its expensive attributes impede its uses significantly. In most cases, MRI machines can cost anywhere from $150,000 to over $400,000 for less complex models. Some models have been valued at over $1 million due to excess componentry or more advanced operating systems and innovative technologies. This is a cost that most health organizations are unable to afford. This large expense also prohibits many governments, especially developing countries, the ability to invest in. Moreover, in Australia, undertaking an MRI scan can range from $150 to $500 as a result of return on investment on the initial expense of the machine. Also, due to the scarce availability of MRI scanning due to their cost, dramatically increases waiting times for patients with non-urgent illnesses. Waiting times in Australia, depending on urgency and location, can take as long as several months. With these factors analysed and interpreted, it can be observed that further development is required across scientific disciplines in order to overcome current limitations. Innovation in magnetic technologies could see a replacement of the current superconductive magnets in MRI machines, reducing costs whilst maintaining or increasing efficiency. Moreover, with both federal and public investment, MRI technology could be subsidized as an alternate to replacing the current magnetic components in MRI machines.